wabarakatuh, and good morning. My name is Muhammad Azizi Hafizi bin Ahmad Nasir. My metric number is 1910611166. Today, I would like to explain about our mini project introduction. So, my part for just this presentation is introduction. So, I will present the introduction for our mini project. So basically, a pendulum facing downward, is an example of a stable system. The force of gravity affecting the mass pendulum stabilizes the pendulum at the position normal to the Earth's surface after an external force has been applied. In contrast, an inverted pendulum or pendulum facing upward is an example of an unstable system. One way to stabilize the inverted pendulum system is by moving the center point of rotation (pivot point) with a proper velocity and acceleration in the direction of horizontal axis. An inverted pendulum system is a nonlinear system. In other words, different system response can be observed by applying the same speed and acceleration. In addition, the inverted pendulum system is an underactuated system, the system which has a lesser degree of freedom of the output than has lesser degree freedom of the input than the output side. The horizontal force at the pivot point as input, root angle and position of the pivot point as the two output variable. Thus, our mini project is basically to apply or use pole placement method to basically as function to stabilize the cut inverted pendulum. That's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Hasib Izrin bin Ahmad Azudin. Metric number 1910611118 will continue with the objective. Based on the lab 2, the cut inverted pendulum system is an unstable system but improved by using the pole placement controller. However, the system outputs produce an enormous error. Thus, the first objective of this mini project is to design a controller to enhance the cut inverted pendulum system with pole placement controller. In the controller design, the system stability can be verified from the system pole location on the complex plane. The system is said to be unstable if one of the poles is located on the right side of the complex plane. Otherwise, the system is said to be stable if all poles are located on the left side of the complex plane. For an unstable system, it requires a control method that can bring all the poles to the left of imaginary axis to become a stable system. For example, this pole placement controller. The second objective is to analyze the design system performance. The control objective is to maintain the pendulum's equilibrium while the cut tracks a desired trajectory. In the presence of external disturbance, the effectiveness of the closed-loop response for pendulum angle and cut position will be examined. It is possible to balance the inverted pendulum and control the cut with more satisfactory closed-loop response according to the findings of computer simulation. That's all from me. Thank you.
Good day, doctor. I'm Sridhan, son of Ilham Kovan. Matrix number 2010611347 will be presenting about the subtopic which is methodology and will be continued with the results of the inverted pendulum system. So I would like to spare some of my time to present about the methodology first. The system is upgraded with a proportional integral PI controller to reduce steady state error. State space from the cut inverted pendulum system with pole placement control is transformed through MATLAB coding because the PI controller function using transfer function equation. Then using the simulink program, a flow graph is created to simulate the output based on the input, which is the Ziegler-Nichols method. To obtain the value of Kp and Ki, these are the steps which is Ziegler-Nichols methods. Step 1, assume K1 equals to 0. Step 2, the new transfer function Kg open bracket S close bracket over H Kg open bracket S close bracket H open bracket S close bracket is then obtained. Step 3 is using the root Hartride table, the value of the K criteria is obtained. Step 4, values of K1 and Ko are obtained from the criteria value. On the other hand, we will be having the MATLAB PID tuning, which is functional for finding the values of PID controls, proportional, integral and derivative gains in order to achieve desired performance, and adhere to design specification is known as PID tuning. PID controller tuning may seem simple, but it might be difficult to identify the set of gain that will provide your control system to obtain performance. PID controllers are often tweaked manually or through rule-based techniques. Manually tuning techniques are time-consuming and iterative, and if applied to hardware, they may result damage. There are significant drawbacks to rule-based technique as well. For example, they do not support models of unstable plants, high-order plants or plants with little to no time delay. Even for plants model that conventional rule-based approaches struggles to handle well. PID can be automatically modified to obtain the best system desired and to meet design requirements. Prior to installs and simulating the control system, the correct value of Kp and Ki must first be established through tuning. We choose the Ziegler-Nichols method and the MATLAB PID tuning software as our two tuning approaches for this project. Next, it will be the results. For the laboratory 2, we obtain two kinds of transfer function, one for the pendulum and another one for the card. By using the MATLAB simulating software, we can construct the signal flow graph of the system by the PI controller. Let's watch a short recap of the video while conducting the simulating operator. By utilizing the Ziegler-Nichols method, we will be able to obtain the K value using the root table for the transfer function of pendulum and card. Furthermore, we will be viewing the output graph performance for the pendulum and card that will be done by clicking the scope in the simulating software. Referring to the graph, we could be able to analyze the output of step input, setting time, peak time, rise time, percentage overshoot, and final value. In accordance, Making use of the PID controller, we could operate MATLAB auto tuning as per below for both the pendulum and card. Therefore, this is the results for the MATLAB auto tuning. These are the values that we obtained for pendulum. Kp equals to 0, K1 equals to negative 125.2. For the card, Kp equals to 0, K1 equals to negative 11.09. We are able to obtain the output of the graph performance consequently for both pendulum and card by using the MATLAB auto tuning. Based on the graph shown, we will be capable in observing the table of output as the step input, setting time, peak time, rise time, percentage overshoot, and also final value. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Danny Ashmawi bin Zulkifli and my metric number is 201062231. I would like to present the discussion part of the mini project. The task that we were given of addressing and improving the inaccuracy of the car inverted pendulum system by adding pole positioning and PID controls at the start were completed. First, all of the data and transfer functions acquired for the inverted pendulum system are identical to those found in Lab 2. We then employed a pole placement controller to regulate and enhance the system based on the transfer function and output graphs obtained from the original system. The original's controllability should be tested using phase variable form to ensure that the system is a controllable system before proceeding with the next stages. The gain K is then computed by comparing the system's compensated and uncompensated values. The PID control is then implemented in the inverted pendulum system with pole placement controller. Using the Ziegler-Nichols tuning approach and the Routh-Hurwitz method, we determine the PID values for the system with pole placement controller. The generated PID values will be combined and added to the system block diagram as a PID controller. According to the findings of this study, the output performance following the proportional integral, which is PI control implemented, met the design requirements to minimize the steady state error, the settling, rise, peak, and percentage overshoot durations. However, had been altered as a result of the PI controls deployment. This is brought on by the PI controls manipulation of the transfer function poles. This issue ought to be resolved by the use of full PID control. The overshoot and time should be fine because the conditions explicitly for the PI control are not stated. The PI controller was used to correct a significant inaccuracy that was present in the original system, which is the steady state. To correct the tempering, overshoot, and time caused by the PI control, it is advised to apply the full PID. Different inputs had no effects on the inverted pendulum's output since the characteristic of a pendulum is that it always returns to its initial position. Regardless of the quantity of inputs used, transient response only depends on the characteristic equation. On the other hand, the card system had reached its ideal operating state, where different inputs would result in diverse system outputs. Additionally, the step 1 input will result in a final value of 1, and so forth. 15. Finding the correct values of Kp and Ki using MATLAB tuning and the calculative approach of Ziegler-Nichols produces a range of results, but each result is effective in eradicating the problem. In comparison to the Ziegler-Nichols approach, TS equals to 4 to 9 seconds, MATLAB tuning tends to result in faster settling times, which is TS equals to 4 to 5 seconds, and a low percentage overrun of 0.37%. Despite the fact that there is no percentage overshoot, the undershot for the card system produces a value of 12.47%, whereas all overshoots for the pendulum system are infinite. In this assignment, the MATLAB program is used to simulate the system output by producing the system's block diagram. The system with merely a pole placement controller and a pole placement and PID controller generates its own block diagram, which is then linked to an oscilloscope. The output graphs of the original system, the system with the pole placement controller, and the system with the pole placement and PID controller are observed and recorded. Following the observation, there follows an analysis of the process and graphics. From the control engineering mini project assignment, we can see that both pole placement and PID controllers are very useful in controlling the unstable system. Apart from that, we can apply both pole placement and PID controllers to either combine them together or separate them to function independently.
Hello, Dr. Hasrizal. I am Syed Yusuf bin Syed Rofli and my metric number was 2010622254. For this mini project inverted pendulum system, I will be presented my part about conclusion. The purpose of this mini project assignment is to improve the stability of the card inverted pendulum system by adding the pole placement controller, PID controller, and so on. Before undertaking system simulation and analysis, it is critical to grasp pole placement control, proportional control, integral control, and derivative control. Aside from that, we may create controllers in a system to maintain the system stability. As a result, for this cut inverted pendulum system with 12% for overshoot and 4 to 5 time settling, it is preferable to use only pole placement controller for the angle output and both pole placement and PID controller for the displacement output to ensure the system output are in their own steady state value. Truth application, simulation and adjusting gain values to see how they affect output performance, we can obtain a better understanding for the P, I and D function in PID control. Although the steady state error was corrected, it is recommended that further PID and LQR control be used in the process to achieve the best system performance. That's all from us, Group 5. Thank you.